Okay, is this better? Yeah. Okay. Yeah, so as I was saying, usually in a math class, you first learn about sets and then you learn about functions between sets. But remember from yesterday that in Lean, we don't use set theoretic foundations, we use type theory. So our functions are going to be functions between types, right? So we can start, for example, with two types, x and y. If we want to define a function from x to y, the notation is the usual notation we will use on the board, maybe. So f colon x to y denotes a function from x to y. If we want to apply this function to an element on the set x, well, we can just denote it the usual way, so f parentheses x. But the parentheses are usually not necessary unless you have a complex expression. So let's look at some examples below. Here I have three types, x, y, z. I have a function f from x to y, a function g from y to z. And I am asking that x is an add money just so that I can add elements of x and show you some examples. So I first want to evaluate f at an element a of x. So I can just write that f of a. I don't need the parentheses. But if I want to do something a bit more complicated, like for example, I want to take the composition of g and f, then if I try to omit all of the parentheses, this is not going to work, right? Because the way that Lean is going to interpret this is it's going to think that I'm trying to apply g to the function f, which of course doesn't make sense, right? So here I do need some parentheses. I need to put the parentheses surrounding f of a. F of a is now an element of the type y. So it makes sense to apply g to f of a. Similarly, if I want to do something like f of a plus b, which makes sense because I can add elements of x, I need the parentheses because otherwise what Lean is going to interpret is it's going to first apply f to the element a. So that's going to be some element of y, and then it's going to try to add f of a, which is an element of y, and b, which is an element of x. And here we get the error that there is no way to add an element of y and an element of x. So parentheses are sometimes necessary, but not if we have like very simple expressions. And we are going to talk a bit about injective and surjective functions. So these definitions are already in Lean. They are in the namespace function. So remember, we organize lemmas in namespaces usually in Lean. So everything about functions is going to be in the function namespace. And if I don't want to write function dot all of the time, what I can do is I can open the namespace, right? So now instead of having to write function dot injective, I can just write injective because I have opened the function namespace. Okay, so as before, we have three types, x, y, z, a function from x to y, a function g from y to z, and I also fix some elements of these sets. Since some of the lemmas that I wrote below are already done in the Mathlib library or in Lean, I want to open another namespace just to avoid any name conflicts. So that's what I'm doing here. And then we are going to check how injective is defined in Lean. So we see that the definition of injective is the usual one. So a function f is injective if given any two elements of x, if f of a is equal to f of b, then that means that a has to be equal to b, right? So the proof of this lemma that I'm writing here is just REFL, which means that this is just true by definition in Lean. And the reason that I'm writing this lemma where the proof is just REFL is because then this allows me to rewrite injective def if I want to replace injective by the definition of being injective. I wrote a couple of other REFL lemmas here. So the first one is evaluating the identity function. So the identity applied to x is equal to x for every element. And then also I wrote a lemma for composing functions. So g composed with f applied to the element x is the same as first apply f to x and then apply g. So all of these are true by definition, but we will use them to rewrite some things in the exercises. Okay, so maybe the first thing that I want to do is I want to prove that the identity function is injective. Okay, so I will use this lemma, rewrite injective def, to replace the word injective by the definition of what it means to be injective, right? And then this makes it clear what the goal is. Now the goal is to prove that given any two elements of X, such that identity of A is equal to identity of B, then A is equal to B. Okay, so whenever we have a goal of the form for all something, we can start with intros, right? So we do intro AB, HAB. So A and B are two elements of X, and HAB is this hypothesis that the identity applied to A is equal to the identity applied to B. And now the conclusion is A is equal to B. Okay, so what I can do next is I can also rewrite the definition of the identity function in this hypothesis HAB. So I can do rewrite eval at HAB. So if I do this, this is going to change the first appearance of the identity. So we get A is equal to the identity applied to B, and then I do it again to also replace the right-hand side. Now HAB is exactly what I want. So I can just do exact HAB. A comment here is that some of these rewrites that I have done, well, all of the rewrites in this case are not really necessary for Lean. Right? So if I comment this line, rewrite injective def, everything works still the same, right? Because Lean can see through this definition. So I can just start doing the intros right away. And similarly here, identity of A is by definition the same as A. So I can omit this line and I can just do exact HAB. However, when you are doing some proofs that involve like very maybe complicated definitions, or maybe you are starting to use Lean and you want to see clearly what your goal is, it's sometimes useful to still do these rewrites, even if Lean doesn't need them. It can be useful for us to see what's going on. Okay, so yeah.
I think yesterday something similar was done using simp only and then the name of the definition.
Yeah, we could also try that here. So we could do zip only eval, and then I only need to write it once.
But you still
right?
need this additional lemma, yes, that you first.
Oh, so you mean just try simp only here?
Simp only with the argument ID, just to unfold.
Oh, with the, yeah. Yeah, that's also work.
Okay.
Yeah. Yeah, I guess we could also write injective, but then this becomes a bit uglier because we get some of the brackets. That's why I wrote the injective def. Yeah. Okay. Okay, so I propose some other exercises about injective functions here. So you can start the same way, write the definition of injective, and then see what you need to, which variables you need to introduce, and what other rewrites you can do, and so on. Next definition is surjective. This is also the definition that you will expect. So F is surjective if and only if for every element in the codomain, there exists some element in the domain such that F applied to this element is equal to the element in the codomain. Okay, so the first exercise is to prove that the identity, again, is a surjective function. Maybe now here, let's do the one about the composition of functions. So we are going to assume that both F and G are surjective. And from this, we can conclude that the composition is also surjective. Okay, so what do we do? Again, I'm going to start by rewriting the definition of surjective, just so that it's a bit more clear what's going on. But I also want to rewrite it in the hypothesis. So I can do this at once by rewriting everywhere. Now, as before, I start by introducing a variable. So I'm going to introduce a variable set. And I want to prove that there exists some element x such that G composed with F applied to X is equal to Z. How can I do this? Well, I can do this in 2 steps, right? So first, I have this hypothesis HG that tells me that G is surjective. So from this, I can get some element Y in the set Y such that G of Y is equal to Z. Okay. I can do this with the tactic obtain. Sorry. So obtain y hy from hgset. So if I do this, this is going to give me the element y and a proof hy that g of y is equal to z. Now the next step is going to be using now that f is also surjective, right? So for that I have to use the hypothesis hf, and I have to apply that to the element y that we just found. Okay, so similarly I'll do obtain x hx, and I obtain this from applying hf to the variable y. And now the element that I want to use in my proof is this element x that we just got, right? So to fill in the existential, I use the tactic use, so use x. Now I have to prove decompose with f applied to x is equal to z. So I'm going to rewrite, the definition of composition. And now I have already an hypothesis hx that tells me f of x is equal to y. So I can rewrite that. Oops. Now g of y is equal to z. This is exactly hy, right? So I can also rewrite that here. Sorry. Here, and then we are done. Yeah, so you have another exercise here about surjective functions, and then the definition of bijective is a function is bijective if and only if it is injective and surjective, and then you can figure out how to prove these two lemmas about the identity and the composition of bijective functions. Okay, yeah, sure. You could also use R cases here. Yeah. Yeah. It's just a different way of writing that, but R cases will also work here. Yeah. Okay. Yeah. So the last part of this file is talking about lambda notation. So in Lean, if I want to define a function, I can use the notation lambda x maps to f of x. So that is the function that sends the value x to the value f of x. So for example, here I can do lambda n maps to n squared plus 3. And also, instead of using the symbol lambda, we can just use the keyword fun. And this has the same effect. So we can do fun n maps to n squared plus 3. Okay, now, for example, if I apply this function alpha to value of 3, then this is going to be equal to 12, just by the way that I define this function. And yeah, if you want to practice with some other concrete function, I define here the function, the successor function, so the function that sends a natural number n to n plus 1. And I asked you to prove that this function is injective, but it is not surjective. Okay? Any other questions about this file? Yeah.
So the injective and surjectivity, this is defined for all types, or did we restrict the type of the x and y to something small?
I think it's defined for all sorts, maybe. So if we do check function injective, yeah, so here you can see the whole definition. So U1 and U2 are universals. So alpha and beta are any sorts or any types if you want, right? And then you can define, yeah, for any function between these two sorts, you can define the property of being injective. So it's either type or prop, I guess. Yeah, just think of it as type, as a type. So it's not restricted to the types x and y that we have fixed at the beginning. This is something that you can use for any type that you choose. Yeah. And yeah. Okay, so now let's talk about sets. Well, sometimes when we are working with functions, we want to define, we want to do, we want to understand the image or the pre-image of a set by this function, right? And usually that's going to be, for example, the image of the function is going to be a subset of the codomain. But here that's not exactly how it works, because in Lean, the codomain is going to be a type, right? But we can still function with the same mental model. So the way that this is going to work is we have, well, let's fix in this file a type omega, right? So omega, you can think of omega as a big set where we are working. And then we can define a type set omega. Set omega is going to be the type consisting on all subsets of this type omega. That means that if I have X is of type set omega, this tells me that X is a set where all of the elements of X have type omega. Okay? So here I'm fixing X, Y, and Z in this type, set omega. That means I can think of X, Y, and Z as 3 subsets of the set omega, which is really a type, but think of it as a set. Okay, and then I'm also introducing some elements. Okay, so we can do all of the usual sets operations that we want to consider. So for example, we can talk about subsets. So we use the symbol contain, which we can type with /sub or /ss. This means that X is containing Y if and only if for all elements in the type omega. If A belongs to X, then A belongs to Y. So you can see that this is the definition just because this is true by refer. And for example, if I want to prove that X is containing X, this is also going to be true by refer. Just because in this case, what this is telling me is that for all A is in X, if it implies that A is in X, right? Which is obviously true. Okay. Now, let's look at some examples of this. So the first example is proving transitivity, right? So if X is containing Y, Y is containing Z, I want to prove that X is also containing Z. So I can start by, again, rewriting the definition of what contains means. So rewrite subset def everywhere. Now, I'm going to fix an element in omega, so intro A, and I'm going to assume that this element A belongs to X. And I want to prove that it belongs to Z. Okay, so what I can do is I can apply these two hypotheses that I have, right? So first I have that A belongs to Y implies A belongs to Z. So I'm going to apply that first. Sorry, it's YZ. Now the goal changed. So before I had to prove that A belongs to Z, but after this apply, I just have to prove that A belongs to Y. Now I use the previous goal, so the previous hypothesis, sorry. So I apply HXY. Now this is going to change the goal to A belongs to X, but this is something that we are assuming from the beginning, right? So now the goal is just exact HAX. Okay. So we have talked about subsets. We can also talk about when two sets are equal. And two sets are equal exactly when they have the same elements, right? And in Lean, we have that as a lemma. This lemma is called set.x is if and only if. X is short for extensionality, which is exactly this, this axiom here. So yeah, whenever we have a goal of the form X is equal to Y that we want to prove, we can just rewrite this set.x if and only if to get this equivalence. And we can also do that by using the X tactic. So for example, here I have X is containing Y, Y is containing X, and I want to prove that the sets are equal. So I'm going to start by doing XA. So this extensionality tactic is going to apply this lemma here. So it's going to introduce a variable a and change the goal to a belongs to x if and only if a belongs to y. Okay. So now, since this is an only if, this is an if and only if, I can use constructor to get each of the two implications. Now, I'll have to prove each of them separately. So for the first one, I want to prove a belongs to x implies a belongs to y. So this is going to be, apply hxy. And then similarly, the other one is going to be apply hyx. Yeah. Okay. We also have other operations like we can take unions and intersections of sets. So the notation is the usual one. And if you hover over the symbols, you can get how to type each of the symbols in line. But for example, for the union, A belongs to the union of x and y if and only if A belongs to x or A belongs to y. And similarly for the intersection, A is in the intersection if and only if it is in both of the sets. Okay, so let's do some exercises here to practice. So for example, I want to see that the set X is contained in the union of X and Y. For clarity, I'll start by rewriting the definition of union. What's going on here? Oh, sorry. I need to do intro A first, of course. Okay, now I have to prove that if A is in X, then A is in X or A is in Y. So I'm going to do intro HA. And then what I have here is exactly the left-hand side of the OR. So I do left, and then exact HA. And as an exercise, you can also do that Y is contained in the union of X and Y, which is going to be pretty much the same, but just right instead of left. Okay. And then similarly, we have some exercises about intersections. So if I want to check that the intersection of X and Y is contained in X, I start by introducing A and I prove that A is in the intersection. So now, if I rewrite the definition of intersection in the hypothesis HA, I see that this is the same as A is in X and A is in Y. So I can use exact HA.1 to get the conclusion that I want. Okay. There's some more exercises about intersection here. Now, the next thing is that we can use the usual notation to define sets. So whenever we have a type X and a proposition P, sorry, a predicate P that goes from X to proposition, then we can define the set of elements X in the type X such that the property is true for X. Okay. Yeah, and this is just the way that we are defining this set. So that means that A belongs to this set is equivalent to A satisfies the property P. Okay, which is what I'm writing in this lemma here. So A is an element of this set if and only if P of A is true. This is true by repo. So for example, 3, I claim that 3 is in the set of natural prime numbers. So I can do rewrite memdev. And then, well, Lynn already knows that 3 is prime. So there's some lemma not prime 3 probably. Yeah, and this tells me that 3 is prime. Okay. For another example, you can later try to prove that 42 is even. So the definition of even is there exists some t such that n is equal to 2 times t. So you just need to figure out what that is. Okay. And now let's connect back to the previous. So
in general, without having to write a lemma like lambda, how could we unfold the definition of something like the membership of a set? So if you do RW lambda without writing the lemma lambda each time.
You don't really need that rewrite because these are equivalent by definition. So you can just write exact 9'3", and this is already going to work. So this rewrite is here for mental clarity more than anything. It's not something that Lean needs. So once you get used to it, you don't need to write it.
Can you somehow see the definition if you don't know it? I mean, how do you look it up?
Sorry, which definition?
Well, the definition of the set membership. Because it's like this complicated notation. It doesn't just have a name.
Yeah, I think you would have to use like the synth stuff.
Yeah, I guess.
You should be able to hover over to the info view and rewrite the name of the thing you see.
You mean, member side.
Rewrite
Yeah.
set int membership.
Mm-hmm.
Then that will unfold the instance, and then it should always fit.
Oh, okay.
So desync set of int membership is click and double click.
Okay, let's try that. Oops.
And good luck copying.
Yeah, set int membership. Okay. Membership mem. What was it? I forgot what it was. Membership set. Yeah. I'm leaving the brackets out. Membership set. Okay.
Try desync.
The same. Okay. Yeah. Okay. Yeah, that works.
Yeah, there you go. So that's halfway there.
Okay. So we do need the desync.
Desync is cheating because it's just using.
Yeah. Okay. Okay. Yeah. So now let's go back to thinking about functions and images and preimages. So if we have a function from A to B, and we have a subset S of A, then we can take the image of this subset, right? Usually in maths, we will use the same notation as taking the image of an element. So we will use F parentheses S. But of course, Lean is not going to be happy if we try to do that, right? So we have to use a different notation. And the notation that we use is F and then 2 primes S. So this is applying F to the set S. So that's going to be a set in the codomain. Is the set of elements in B such that there exists some element in A that belongs to the set S and such that F of A is equal to B. This is called set.image in Lean. And similarly, we can also take preimages of sets. Again, we have to use some special notation for this. The notation is F to the -1 prime. And then when we do that, we get the set consisting on elements A of A, such that F of A belongs to the set B. And this is notation for set.preimage. Okay, so let's look at some examples of how to manipulate this. So, yeah.
So we said that S in the previous example is a subset of A, right? But A is not a set.
A is a type. Yeah.
So what if I were to write something like G colon set S? Would it be a subset of S, or would it be a set which elements have type S or something like that?
So if you do set S, you are casting S to be a type, and then you are considering a subset of S. So the elements will have type S, they will not have type A. Does that make sense?
So if, for example, the inclusion would not be true between G and S in this example, right?
Right, you will have to take some coercion maps, I guess, yeah. Yeah, because the set A and set S, for example, these are different types, right? So one is subsets of A, the other is subset of S. Yeah, so I'm being a bit loose with language here. I'm just, the mental model that I keep is that A is my big set and then S is a subset of A. But you are right, A is really a type and S is a set in which all of the elements have the type A. That's really what's going on. Yeah. Okay. So, okay, let's check that the set S is contained in the preimage of the image of S. Okay, so let's start with the intro. So intro a variable A, and then let's assume that A is in S. Now, I want to prove that A belongs to this preimage. So there's probably going to be some lemma that tells me that something belongs to a preimage, and this is probably going to be called set.memPreimage. Okay, so now when I do this rewrite, this tells me that A belonging to the preimage is the same as f of A belonging to the image. Okay? And now I can play the same game. I can ask Lynn, okay, what does it mean for something to be in the image? So I can do rewrite set mem image. And this tells me that there has to be some element in the type A such that this element belongs to S and f of x is equal to f of A. Okay, so what is this element? It's just A, right? So I can just feed it to Lynn. So I can use A. And it's going to be smart enough to figure out that because we already have this hypothesis A is in S, this finishes our goal. It's going to automatically check that it satisfies the properties. Yeah.
You also have written something like decent instead of remembering these names of the rewriting rules?
Here,
Yes.
I guess I can try sim and see what happens. Yes. Yeah, but simp is just doing simp only these two lemmas. Yeah. Yeah, so if you don't know the names, you can just try maybe rewrite as well. I'm not sure. Yeah, you could also try to write with interrogation mark, or usually just try simp, I guess. Yeah. Okay, so maybe I'll change this. And now we just have to use it. Okay.
Is it about the -1, like
Yeah, so if you don't know how to write a symbol, you can just hover over it, and it will tell you different ways of writing it, right? So usually I write this with /int, but you can write it using each of these ways, okay? Okay. Yeah, and that's almost everything I wanted to say. I also added a couple of exercises about universal and existential quantifiers just to get more practice with logic. But yeah, I probably gave you more exercises that you will have time to do. So just pick which exercises are more interesting to you and do those. On the other hand, if you run through all of the exercises, there are more exercises in the book, Mathematics in Lean, so you can also try those. But yeah, I think this is everything I wanted to say. If you have any questions now, I'm happy to answer. No? Yeah.
So how does one write something more complicated, like a function which maps to another function? So how can we write this as a definition of the type?
A function that maps to another function. What do you mean?
So a function, taking a function, giving another function.
Oh, so you mean you want to pass arguments to the function, or?
Yeah, for example. I'm just not sure how one would write the type properly.
used to just do opening bracket and then A arrow B closing bracket arrow
Yeah.
opening bracket.
Okay, so one just nests all of this stuff. One just is nesting all of this stuff.
Yeah.
Yeah, I mean, you can also write it, I guess, explicitly if you want. So you can pass the argument, for example, a function from, I should be here, from A to B, and then you want to output another function, I don't know, let's also say from A to B, because I don't remember which variables I have open, but yeah. So this, yeah, this will also take this function f as an argument and produce another function. But yeah, you could also just write, this will be equivalent to write an example A to B to A to B.
If you write it in that way, how does this lim understand these A and B? These can be also propositions, right?
A and B are two types that I define here.
In case it seems it's correct, right? Even if you write it that form, the last exercise.
Sorry, what do you mean?
I mean that you are taking either types of propositions in lim, right?
No, A and B are not propositions. A and B are types. Yeah. Yeah.